right. Smell that? You taste that? I just ate. All right, so taste. I'm gonna draw a tongue here. There's a tongue. And on that tongue, we have various receptors here. I'll draw 3 receptors. I should probably draw better than that. It's terrible. All right, we're going to talk about taste. So when you eat something, we eat chemicals basically, and those chemicals will dissolve in the saliva and they'll bind on a few different types of receptors. We have sour, salty, and sweet, umami, and bitter. Okay. We're going to first talk about sour taste receptors. So sour things are acidic. So here we have a calcium voltage gated channel right there and a calcium voltage gated channel right there as well. So when you eat something sour, say a warhead, the acids in the warhead that make it sour, they'll dissolve in your tongue. And you know what acids have? They donate protons, right? Well, these protons will travel through this proton channel. And the thing about taste receptors, I guess I should mention, is that they will never initiate an action potential within the receptors themselves. Rather, they'll just modify the signal below threshold, something like that. So, sweet proton enters the cell. And in here, we have neurotransmitter. We don't actually know what the neurotransmitter is, but we have neurotransmitter, and we have snare proteins right here. You know, snare proteins that are activated by calcium? Yeah. We have neurons and such. So neuron. Neuron, whatever. Just a neuron. Something like that. I don't know. That's my neuron. Okay. All right. So basically, what they're trying to do is, as in all receptors, as we know, activate the snare protein. Boom. You release neurotransmitter. You stimulate the neuron, and you send action potentials. So protons will come in here, and protons are positively charged. They will raise they'll depolarize the membrane a little bit, not above threshold so that sodium rushes in, but rather just enough to open up this voltage-gated calcium channel. And calcium will come through, it'll activate the snare proteins, and then you'll get neurotransmitter, which then sends an action potential. That's how sour taste receptors work. All right, let's talk about salt. All right, here we'll just have a salt channel. So salt usually would be like a cation, so like sodium, potassium, magnesium even, I think this is a monovalent cation channel. And so most commonly, we salt our fries with sodium. Interestingly enough, in the 50s, they had lithium chloride that you could use, lithium salt, until we figured out that lithium in high amounts in the body is bad for you. It also has medical purposes as well for depression. But most of the time it'll be sodium. There is actually potassium chloride as a substitute, but that could be dangerous. More dangerous than sodium. As we've learned, as potassium really messes up membrane potentials. Okay. Sodium will diffuse through. Potential will go up a little bit, not above threshold, sorry, but just enough so that calcium enters into the membrane, activates these snare proteins. We get fusion of the vesicle, and then we get neurotransmitter action potential. That's how a sodium receptor, or a salt taste receptor works. Okay, now this one's a little different. G protein. All right. So here we have, these two pathways right here, they're ionotropic, or they're just ion channels pretty much. Here we have a metabotropic pathway, or it requires a ligand to bind. So there's our binding spot, and this is a G protein coupled receptor. You know what those are. Alpha, beta, gamma subunits. So you'll have a sweet ligands. So the sweet receptors, they'll bind ligands that are like sucrose, for example. Bind it. Oh, it's sweet. Umami would be like a compound like MSG, for example. Other amino acids that you would find in meat. MSG just stands for monosodium glutamate. And bitter would be, for example, like a calcium ion or quinines or quinones or whatever. That's organic chemistry crap, I don't care. So, basically you have a chemical that binds to the G protein coupled receptor and initiates a response. The alpha subunit will dissociate here, and it'll activate phospholipase C. And then this will actually go and cleave phosphoinositol. It's a lipid in the membrane into DAG, which is another secondary messenger that we don't need to worry about for this pathway, and IP3. IP3, this is the important one, because IP3 will go and it'll activate this calcium channel in the smooth ER, unleashing loads of calcium, which will then go and bind to snare proteins, causing neurotransmitter to release, and then an action potential. One difference to note is that these two receptors, these ionotropic taste receptors, they require extracellular calcium to function, whereas this guy uses intracellular calcium. But that is why we taste. That's how we taste, at the cellular level. Thank you. Okay, sweet. So here I got a nose. Awesome. There's a little opening to the nose. Here is the top of the nose. There's a little really thin piece of bone. Here's the olfactory bulb, where the neurons kind of clump together as smell neurons, sense of smell neurons. and they'll just poke on through right through the bone here. So all the tissue, and then you have your nasal epithelium right there. So let's zoom in on a single neuron. Okay, let's go. Let's do it. All right. Here we go. Here's a neuron. Here's our bone up here. Me sticking through. I'll continue on. All right. Here's our neuron. Just blue. Here's our neuron. I'm sure it'll be bigger than this, but I'm just gonna draw something kind of ugly. Okay. Sweet. G protein coupled receptor, ligand pocket or something right there. Looks like a tyrosine kinase receptor. I promise it's not. Okay, sweet. We have our. Okay. Now it's closed. Okay, so within the epithelium surrounding, there's cells surrounding these neurons that they poke through, supporting them. There's mucus, right? So what will happen is an odorant will come in. Here's our odorant. I don't know. Could be something. I don't know. Here's our odorant. It'll dissolve in the mucus, and then it will bind. And upon binding, this is a G protein coupled receptor. The alpha subunit will dissociate. Oops, that's a terrible color. Give me a better color. Alpha subunit will dissociate, and it will activate this enzyme here called adenylyl cyclase. And that will convert ATP to cyclic AMP. So we'll get cyclic AMP. And then that will go and activate sodium channels. Those sodium channels will allow sodium to come in and initiate an action potential down the neuron, which gets sent up to the olfactory bulb. Doesn't have to pass through the thalamus. That's just why we associate smells with memory, because it gets processed right by the part of our brain that processes memory. And so that is in a nutshell how our sense of smell works chemically. Now we're going to talk about how we hear. What's interesting about our ears, we've talked about how the receptors on our tongue and our nose, and they convert chemical signals into electrical signals that our brain can interpret. The interesting thing about receptor cells in the ear is that they convert mechanical signals into electrical signals. Mechanical, so it's something completely different. So I'm going to draw a cell here. This cell has hair. It's a very hairy cell. These are the inner hairs, and these detect movement of sound waves. So these are located in your inner ear. So as sound travels, it goes through the outer ear, hits a tympanic membrane, vibrates, goes through the oval window, through the basilar membrane, all the way up through the utricle, I think the cochlea or something. I don't know the anatomy. And it will stimulate these inner ear cells. Now, I'm going to draw this out real quick. Just be patient with me here. neuron right here. We have these, which are full of neurotransmitter. So we'll have voltage gated calcium channels as well. Okay. So you might be asking, why are we using potassium channels instead of sodium? Well, to answer your question, potassium's driving force is actually to go into the perilymph. And why is that? That is weird. The concentrations are actually quite similar. The reason is voltage. There's a 120 millivolt potential difference between the endolymph and the perilymph. And so the potassium's driving force is to go through the cell into here. So, how does that work? How do the potassium channels open? They're mechanically gated. So, as sound pressure waves will move these hair cells, we'll get oscillations, right? So you'll get the cell over here, and then the cell will come over here, you know? And as it moves this way, as it oscillates, it'll opens channels, potassium channels. And as potassium channels open, as they're moved, potassium will flood in. And when potassium floods in, it causes depolarization. Potassium is positively charged, which causes these voltage-gated calcium channels to open, and then calcium will come in. And then you got snare proteins here. Snare proteins are active by calcium. Calcium activates them. And then you got your release of neurotransmitter onto this, to the neuron, and then you get inaction potential. That, simply put, is how receptor cells in the ear work, converting mechanical stimuli to electrical signals. All right, let's move on to the eye. Eye is super cool. So here's our eye. Be patient with my drawings. It's not very good. Gets the job done, though. That's all we need. Get the job done. Get her done. Okay. Go. All right. Sweet. All right, here we go. Cornea. We have this, I'm going to draw some more. The ciliary muscle. Let's draw our lens. I'm drawing blue. Yeah, something like that. It's not very pointy, but actually, move this over here. Boom. Boom. Something like that. Okay. And then there's filaments right here. Connect the eye to this sphincter, to this sensory movements. Boom. There's our eye. It's very oblong. If you had this eye, you'd probably have hyperopia. Okay. So here's our object. Okay, saying hi to us. All right. Okay, so I just need to tell you how this bends light onto that. So probably draw our optic nerve. You know, optic disc. Okay, here's the retina. Okay, cornea, boom, lens, boom. These are called suspensory ligaments. These little stringy things, those are suspensory ligaments. And then this is called the lens. Okay. So, those are the basics. I mean, there's plenty of eye anatomy, but these are what we need to know for what I'm going to teach right here. So, we look at an image. Let's say this guy is coming at us and he's about 5 feet away. Well, I guess how images work is we have the light coming in, and as the light comes in, this cornea will bend it, and then the lens will bend it even more accordingly, and it'll line up right here on a point on the retina so that we see an image clearly. So we want to form the image on the retina, that way our cones can see it and we can see it clearly. Because right here you have the fovea, this area, like the central area of the eye. And that's where most of our cones are. There's two different types of photoreceptors. We have cones and rods. Rods are more sensitive to light, but cones are more clear, more crisp, and we use them in our day-to-day color vision. Rods we use mostly at night when we're trying to see, just enough to distinguish things. Okay, so in low light conditions. So we want to form that image there on the fovea. That way we have a clear image right in front of us. The reason why your peripheral vision is so blurry is because you have rods mostly out there. So, and they're bleached. Your brain fills in the thing. All right, so let's say this guy gets closer. And let me erase this light ray. Actually, no, it's going to be the same. We're going to want to, it's whatever. So if the guy gets closer, right here, say he's closer now. Hi, he's like 2 feet away from you, and it's kind of weird. So what will happen to focus on him is your pupil will constrict, and then this lens will get fatter to bend the light even more to focus it on the retina. And for this lens to get fatter, this muscle right here, the ciliary muscle, will contract. And as it contracts, these suspensory ligaments flatten out, and you get a clear image up close. All right, say you're running away from this guy, and he's way over here now. As he gets out, and he's farther away, and you want to focus on him, what will happen is pretty much the opposite. The lens will flatten like this. Rather than get thicker, it'll flatten as the ciliary muscle relaxes. And when it relaxes, these suspensory ligaments become taut, and then you can focus a far away image on your retina. And of course, if you have like a disorder or something like myopia, which is nearsightedness, the doctor will prescribe you some concave lenses to bend the light to compensate for your eyes' error. So, yeah. Sweet. That is the eye and how it bends light. Okay. Hello. My phone was dying, so I had to put it on a charger. Go to St. George. I'm trying to get this done. Okay. So, now we're going to talk about rods and cones. Rods and cones. Okay, the photoreceptor cells. Sweet. Located on the retina. Awesome. So, they do very similar things. Like they're basically the same thing. There's just some key differences. So I'm just going to show you one. Okay, boom. Actually, no. I shouldn't show you that way. Okay, fine. Here. All right, here, photoreceptor cell, right here. I'll just draw it like a box, something like that. Here's another cell. And here is the neuron. Okay. I'm just trying to draw out the full cell for us here. Might take a while. Okay. So I got enough to get started. All right. So this is our basic photoreceptor. So within this G protein, interestingly, this G protein doesn't actually have a receptor to bind a ligand. Why? It's pretty hard to bind photons, I'd imagine. They're very small. So what we use instead is this molecule called retinal. And it has like 1, 2, 9, 10, 11 is trans, cis, sorry, something like that. I don't know, it's a weird looking molecule, it has like a double bond right here. And so, it's getting into organic chemistry again, yuck. But anyways, this is the molecule, it has like a little double bond right here. It's a derivative of vitamin A. And so what will happen is, this is what we have instead of like the receptor on the G protein, is light, when a photon strikes this becomes trans, or it'll look like this instead. From cis to trans, so it switches up the isomerization of retinal here, and that'll serve as our secondary messenger. It'll leave. So basically, I guess to start is, I'm just going to show you what it looks like in the dark. So usually in the dark, we have this thing, cyclic GMP gets made. And this basically activates calcium channels, which then, activates snare proteins, and then we have glutamate that'll get released. And this is when it's dark, mind you. And as this glutamate releases, it'll bind to this mGluR6 in the bipolar cell, and then an alpha subunit of this G protein will go, and it will inhibit the tryptophan sodium channel, basically preventing sodium from entering and depolarizing this bipolar cell and causing an action potential in this neuron. So, all right, what happens then if light comes to play? Well, basically, if light comes into play, we have this all-trans retinal, and this G protein, the technical name for it is rhodopsin. So this is opsin. Retinal, light strikes it. It goes to all trans retinal. And then the alpha subunit of this will activate phosphodiesterase. And then that will break down cyclic GMP. GMP taking it out, preventing calcium from coming in. That stops. And glutamate doesn't get sent to the bipolar cell. And when that happens, we don't have inhibition of this key ion channel, And so sodium will flow in and cause an action potential, which will, calcium, open calcium ions here, and then glutamate will go and it'll bind to this AMPA channel on the neuron, the ganglia is what it's called, and then sodium will rush in and initiate action potential. So that's how photoreceptors work to initiate action potentials. And it's the same thing for cones and rods. The only thing is that you can have multiple rods. So these are my rods. And they'll have one neuron that innervates them, that they send information to. Whereas cones, I'm gonna draw my best cone. Something like that. I forgot how to draw a cone. I remember in grade school or something. Oh, something like that. Cones are innervated by one neuron. That's why cones are so much more clear. Rods are a lot more sensitive because, it only would take one rod to be stimulated to stimulate that neuron. Whereas cones are a lot more clear for that reason, is that we have more information. So that is basically in a nutshell how photoreceptors work. Okay, well, my phone wasn't recording. So, all right, here we go. Take 2. Let's do this again. All right, awesome. Okay. So, I don't even know where to start. Okay. Within our brain, we have these receptive fields, okay? They can either be off-center or on-center. And if they're on-center, they're off surroundings. And if they're off-center, they're off-center, they're on surroundings. If they're on-center, they're off surroundings. It's the opposite. So, just because I'm fun, I drew you the off-center first. So, yeah, perfect. So, if this guy's dark, basically light won't come in here. Light won't come in here. Rhodopsin will stay in. Cyclic GMP will stay doing its thing. This won't get activated. Cyclic GMP will be like, hey, to the calcium sodium channel, hey, you guys want to come activate some snare proteins? Yeah. Glutamate will come in, bind here to this AMPA channel. Sodium will come in, cause a depolarization here, action potential. Calcium will come in, boom, boom, snare proteins, boom, more glutamate, boom, sodium, boom, action potential. That's for an off-center cell. Surroundings are on, so they don't inhibit this process at all. In fact, more glutamate gets produced. So, yeah. All right, same situation. Say we got a on-center, off surroundings. Well, something would change. This right here, boom. I gotta erase all this crap, okay. It's fine. All right, boom, this will change. We got this protein called mGlur6, and then this tripum protein thing, boom. So, as I explained previously about photoreceptors. So on center, that means the light will activate it. So if it's dark, glutamate, boom, inhibits that. You have the alpha subunit coming in, inhibiting that, no action potential. These light, they're not really doing anything to inhibit this, so you don't get any action potentials in this case. But say, we're like, all right, screw it, all dark. Everything is dark, 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 dark. So what will happen? Well, glutamate. Glutamate. And here we have an anion channel that then these horizontal cells, what they're called, they'll release GABA. Might have heard of GABA before. Gabapentin, boom. GABA activate this anion channel, which will release negative charge, hyperpolarize the cell, cause less glutamate, which means less inhibition, which means action potential, slight action potential, which means a little bit release of glutamate and a little action potential. 2 would be the action potentials, is how we sum it, because about 40% comes from the surroundings and 60% comes from the center. So that, in a nutshell, is receptive fields. It's super cool because the reason why I can see edges is because of these receptive fields. Within the fovea here, that's where we have most of our receptive fields. We have a ton within. And then as you go out, they get bigger and bigger, which is why our peripheral vision gets a little blurry. So, super cool. I would tell you more about it, but I'm tired. I already gave a 10-minute spiel on it, and my phone stopped recording. So, have some mercy on me. Thank you. Okay, I'm going to move on to the next section. Alright, I'm at my grandma's house here. I already kind of explained, like, on the cellular level, how, like, the ear cells, like, transform mechanical signals from pressure waves into electrical signals. And now, just to finish things off, I'm going to show you how those mechanical signals actually get into the ear. So here's an ear. Okay, it's not a very good ear, but basically sound gets in as a wave here. It's a pressure wave, right? Comes in here, and then we have this place called the tympanic membrane. Connects the incus, stapes. Then we have this part called the oval window right here. And this oval window is very skinny, so when a wave comes in, the oval window will actually amplify it because of how skinny it is. And then we get this structure here called the cochlea. And the cochlea is where the magic happens. And so let's zoom in on the cochlea here. So we're going to go down here. This is the inside of the cochlea. Now within the cochlea there's a membrane called the basilar membrane. And if I were to take it, it's kind of like runs along the side of the cochlea like this. Basilar membrane goes up through here. Now if I were to take it and to like wring it out like a sleeping bag, it would look something like this. Here, let's go right here. Be really skinny at the front and really wide at the end. That's what more or less what the basilar membrane looks like. You see? And basically as the sound wave enters the cochlea, it gets converted into fluid waves, and the fibers here, there's collagen fibers that run all along this basilar membrane. These ones will pick up high frequencies, so high pitched sounds, and these ones will pick up low pitched frequencies. They'll resonate, and so that's why old people or older people who have hearing loss, they have a hard time hearing high sounds, because all sound waves will activate those high pitch frequency fibers first. So let's get an inside of the cochlea here. We got the cochlea. Here we got this bottom layer is the scala tympani. Top layer here is the scala vestibuli. And then within we have the scala media. Filling up the scala tympani and the scala vestibuli, we have the perilymph.
And let some of the cool air come out.
And within the scala media, we have the endolymph. Alright, now I'm going to take this ear and we're going to zoom in. We're going to take a cross section right there. So here we go. Okay, so here we got the scala vestibuli. Here's a tectorial membrane. This is the cochlear duct right in here. And then we have the scala tympani. And if we zoom in even further, we have our hair cells right here. These are the outer hair cells within the cochlear duct. We have the inner hair cells. Now basically, as I explained, you know, sound wave will cause these to bend, and then we have these mechanically gated ion channels allowing potassium to flow in. Now, there's this little part right out here between the scala vestibuli and the scala tympani where we have sodium-potassium pumps, where potassium gets pumped in and sodium gets pumped out. So the ion concentration of potassium is really high in here, which provides a driving force for hearing. And so that is on its anatomical level how mechanical waves get converted into electrical signals in the ear. And then, yeah, I explained that earlier in the video. So thank you.